This is the notebook where a raw pre-trained model first learns to act like an assistant. Supervised fine-tuning is the very first stage of the whole RLHF pipeline, the step that happens before you ever touch a reward model or run PPO. We are going to build the entire SFT pipeline from scratch, from raw instruction data all the way to a model that follows instructions, and then compare it to the library everyone actually uses. By the end, you will understand every moving part, which is exactly what a frontier lab interview probes first. Here is the core idea in one breath. Pre-training teaches the model to speak the grammar, the facts, the reasoning patterns it soaks up from the whole internet. Supervised fine-tuning teaches it to be a helpful assistant, to follow an instruction, answer a question, and match a desired format. So pre-training gives it the knowledge, and SFT gives it the manners. And the surprising part, which we will keep coming back to, is that the manners are mostly in the data, not in any clever algorithm. Let me say the key insight directly, because it trips people up. SFT uses the exact same loss function as pre-training, plain next token prediction, ordinary cross-entropy. There is no new objective. What changes is the data. Instead of raw internet text, you train on a carefully curated set of instruction and response pairs. So if someone asks you what loss SFT uses, the answer is the same one pre-training uses, and the real story is the dataset behind it. The notebook lays out the three formats you will meet over and over. The alpaca format keeps it as plain fields, an instruction, an optional input, and an output. Chatml wraps each turn in start and end markers and tags every message with a role, system, user, or assistant. And the llama chat format uses its own instruction brackets with a system block tucked inside. They look different on the surface, but they are all just ways of marking where the human stops and the assistant should begin. And here is the point the notebook drives home. The specific format matters less than being consistent with it. The model learns to read those format tokens as a signal, a little mode switch that says, stop predicting random text, start generating a response. Pick any reasonable format and use it everywhere, and the model will learn the cue. The one thing you genuinely cannot get wrong is what comes next, computing the loss only on the response tokens, never on the instruction. So let us look at the single most important detail in the whole pipeline: label masking. You tokenize the full sequence, the prompt plus the response together, because the model needs to see the prompt as context. But for the loss, you set the label of every prompt token to -100. That number is special. It is PyTorch's ignore index, and the loss function silently skips any position with that label. The result is that the model reads the instruction, but is only ever graded on the response. The clever bit is how the code finds where the prompt ends and the response begins. It tokenizes the prompt by itself, and the length of that gives the boundary. Then the labels are simply -100 repeated for the whole prompt length, followed by the real token IDs for the response. Padding at the end is masked too, also -100, so the model never wastes effort predicting filler. When the notebook prints the tokens next to their labels, you can literally see the masked region flip over to a real label exactly at the boundary. Now why bother? Why not just train on everything? 3 reasons. First, every bit of gradient signal goes toward learning good responses, the thing you actually care about, instead of being spent predicting the instruction. Second, it stops the model from memorizing instruction patterns. You want it to generalize to brand new instructions. And third, it lines training up with how you use the model. At inference, you hand it the instruction and ask only for the response. Mismatch that, and you are training the model to do something you never ask it to do. This is also one of the most common bugs in real SFT pipelines, so it is worth burning in. If you forget to mask the prompt, the model spends capacity learning to predict the instruction text, which you already provide for free at inference. Worse, it can start generating instructions instead of responses, because that is part of what you trained it to continue. A single token offset in the masking can quietly waste an entire training run. When an interviewer asks what breaks if you skip masking, that is the answer. A small but real gotcha in the setup. The notebook uses tiny GPT-2, and GPT-2 ships with no padding token at all. So the code sets the pad token to be the end of sequence token, a standard move. It also points the model config at that same pad. It sounds trivial, but if you skip it you get crashes or silent misbehavior the moment you try to batch sequences of different lengths together. Little plumbing like this is exactly the kind of thing that bites you in practice. Here is the insider truth the notebook flags. At Frontier Labs, SFT data quality is considered more important than quantity. Anthropic and OpenAI hire teams of expert annotators, people with deep domain knowledge in math, coding, and science, to write high-quality demonstrations. The Lima paper made this vivid. Just 1,000 carefully curated examples beat a model trained on 52,000 noisier ones. So in an interview, signal that you understand the bottleneck is data curation, not algorithmic cleverness. Now we build the training loop by hand, no framework, just PyTorch, so you see every step. It is the ordinary supervised loop. Pull a batch, run a forward pass with the input IDs and the masked labels, and Hugging Face hands back the cross-entropy loss for you. Then zero the gradients, backpropagate, clip the gradient norm for stability, step the optimizer, and step the learning rate scheduler. That is the entire engine. If you can write this from memory under interview pressure, you have shown real depth. Watch the hyperparameters because they are deliberate. The learning rate is around 5 times 10 to the minus 5, and the model trains for just a few epochs. That is roughly 10 times lower than a typical pre-training learning rate. The reason is delicate. You are nudging an already capable model, not building one from scratch. Push too hard and you damage the very representations that make the model useful. So SFT is gentle on purpose, low learning rate, few passes over the data. The schedule is worth a beat too. It starts with a short linear warm-up, ramping the learning rate up over roughly the first tenth of training, then decays it back down towards 0. Warm-up keeps those early updates from jolting the model while the optimizer is still finding its footing, and the decay lets training settle into a good minimum at the end. It is the same warm-up then decay shape you see almost everywhere in modern training, and the notebook plots it so you can see the little triangle. Then the notebook opens up exactly what that label's argument does under the hood, so you can explain it cold. The model outputs logits at every position, and the logit at position t is its prediction for the token at position t plus 1. So to line predictions up with targets, you shift, drop the last logit and the first label. Then you run cross-entropy with ignore index set to -100, which throws out the prompt tokens and the padding automatically. Reproduce that by hand, and you will never be mystified by the framework again. And the per-token view makes it concrete. The code computes a loss for every position without reducing, then shows that the masked positions, the instruction and the padding, contribute exactly nothing. The final number is the average loss over only the response tokens. That detail matters. The loss is a mean over the tokens you actually graded, not over the whole sequence. So a long prompt with a short answer is not diluted. The model is scored purely on how well it produced the response. After the from-scratch build, the notebook shows the library version, Hugging Face TRL. You hand the SFT trainer a model, a dataset of text strings and a config, and it collapses the whole loop into a few lines. It tokenizes for you, handles batching, runs the training. The point is not that the library is magic. It is that you now know exactly what it is doing inside because you just built it yourself. That combination, depth plus knowing the tools, is what signals you can actually ship. The notebook puts the two side by side in a table, and it is worth memorizing what TRL abstracts away. Tokenization, automatic. Label masking,